Total knee arthroplasty, or TKA, is one of the most common and effective surgeries in modern medicine. It has restored mobility and improved the quality of life for millions of patients worldwide. As medicine advances and societies age, the demand for TKA continues to rise, offering hope to those who suffer from severe joint disease. Prosthetic joint infection, or PJI, is one of the most dangerous complications of artificial joints. Every year, thousands of patients suffer painful revision surgeries and long term treatment. Additionally, PJI is tightly linked with modern health issues, diabetes, obesity, and aging populations. As this factor rise, the risk of PJI will only become greater. What makes PJI so difficult to treat is bacterial biofilm. This protective layer of polysaccharides, proteins, and DNA shields bacteria from antibiotics and the immune system. Once biofilm forms on the implant surface, traditional treatments are almost powerless, often leaving surgery as the only option. As an agent team concerned about medical challenges and infection, we believe we cannot ignore this problem. That is why we propose an innovative solution, biofilm. Our team is engineering E. coli to be equipped with a thermal switch and will release biofilm degrading enzyme above 37 degrees Celsius. Dispersing B for polysaccharides, protein escape for proteins, DNS1 for DNA. Together, they break down the bacterial castle, allowing antibiotics and immunity to fight back.
So how exactly do our engineering bacteria break down biofilm? Let me walk you through the system step by step. Our goal was to build a mixed-strain bacterial system capable of producing and releasing biofilm-degrading enzyme in a controllable and safe way. The entire experiment can be divided into three parts: enzyme plasmid construction, kill switch chain construction, and biofilm formation and degradation. We first construct plasmid carrying three selected enzymes known to degrade different components of Staphylococcus aureus biofilm. These enzymes are DNase-1, which break down extracellular DNA, dispersin B, which target the polysaccharide PNAG, and protein SK, which cleaves structural mixture protein. Each enzyme was cloned into a IPTG-inducible plasmid so that we could control the expression precisely. But producing enzyme alone wasn't enough. We also needed a system that could release them to the biofilm and also needed to concern the biosafety issue. That's where our kill switch design comes in. To safely release the enzymes and prevent live bacterial escape, we implemented a temperature-trigger self-lysis system using lambda C1857. At 30 degrees Celsius, C1857 keeps the lysogenic state by repressing PR and PL promoter. When the temperature rises around 43 degrees Celsius, the repressor inactivates. Lytic genes such as holin and endolysins are expressed, and cells lyse, releasing intracellular enzyme. With the safeguard in place, we built the rest of the chassis. We isolated the T7 RNA polymerase genes from BL21DE3 and cloned it into the low-carbon plasmid PCL9020, minimizing burden and leakness before heat induction. Function was verified by co-transforming PCL9020 T7RNA-P with the T7GFP reporter into E. coli top 10 strain. After IPTG induction, colonies showed green fluorescence under ultraviolet, confirming T7 promoter activation. We then moved PCL1920 T7RNA-P together with our enzyme plasmid into E. coli MG1655 lambda C1857 to couple heat trigger lysis with T7-driven expression. With these chassis in hand, we measure their lysis timing. Cultures were grown at 30 degrees Celsius to OD600 around 0.6, then induced with 0.5 millimolar IPTG and shifted to 40 degrees Celsius. The OD value stabilized around 2 hours after upshift to 40 degrees Celsius, dropped rapidly between 4 to 6 hours, and reached a minimum by 6 hours. This gave us a hint for the reaction time of biofilm assays. To mimic clinical scenarios, we formed 24 hours mature Staphylococcus aureus biofilm in 96 well plates. For degradation test, strain will induce at 30 degrees Celsius for 4 hours. Normalize OD600 value to 1. Mix at defined ratios. Then apply to 24 hours preformed biofilms. After that, we shifted the plate to 40 degrees Celsius to trigger lambda C1A57 mediated lysis and let the enzyme be released. After the enzyme reacted, we washed the plates, staining with crystal violets, and read the OD value at 600 nanometers. Degradation at regular intervals. The strongest reduction appears around 5-hour reaction time. Dispersing B and DNase1 were effective individually, whereas Protease K showed minimal impact under these conditions. Notably, mixture of dispersing B and DNase1 showed little added effect at 5 hours, but produced significant biomass loss at 24 hours across ratio, indicated that they may have time-dependent cooperation. Overall, we moved T7RNA-P to low-copy PCL1920, achieved stable coexistence with the lambda C1A57 kill switch, constructed inducible enzyme plasmids, and established a reproduced Staphylococcus aureus biofilm model. We also observed a potential dispersing B and DNase1 synergy that strengthened over time. In the next step, we refine the timing to maximize this synergy and evaluate the platforms utilized against device-associated infections.
So how can Dry Lab contribute the improvement of the entire project? We have developed a pipeline that ensures user can get a completely new enzyme just in few simple steps.
We built a protein design pipeline combining AlphaFold 2 and transformer decoders. Users input a target sequence or design objective, and our system generates candidate structures automatically. We evaluate structure confidence using PLDDT scores, and we also apply refinement steps to improve reliability. We include an alignment module based on MN sequence too. This module retrieves homologous sequence from large databases like Swissport, which helps in assessing sequence conservation and guiding design choices. Next, our docking module uses AutoDock-VINA. Once we have candidate structures, this module predicts how the designed protein might bind to a target molecule to reduce manual effort. We wrote an automation script that detects potential binding sites and then draws docking grid blocks automatically, so users don't have to manually specify binding regions. Finally, this system also offers an accessible interface so that biologists can input designs and interpret results without deep computational background.
During our wet lab experiments, we found that under various conditions, it is difficult to determine which condition yield the best results. For instance, if we aim to precisely control an experiment at 37 degrees Celsius to find the optimal enzyme ratio, this is often an extremely challenging task in wet lab setting. Therefore, we combine data from both wet lab experiments and synthetic data to create a machine learning model.
Experiments are precious. What if a model could point us to the right enzyme mix before we pipette? That's why we create ENZMix. We use 3 enzymes, dispersing B, DNase1, Protease K. The ratio matters, but testing every combo is slow and costly. Our main goal, let ML suggest optimal mixture and top 3 mixes to try next. Trained on past plates. An XGBoost model predicts biofilm removal from the 3 ratios and reaction time. A random forest sample gives uncertainty and 95% intervals. This feature finds the single best combination for maximum biofilm removal. It uses an optimization search that scores potential experiments by their predicted success plus and uncertainty bonus to balance high performance with exploration. The result is a single top recommendation. This feature uses active learning to find the most informative experiments for improving the model. The search prioritizes areas where the model is most uncertain, aiming to gather the most valuable new data. After applying diversity filters, it returns a top 3 list of informative experiments to run next. How can you use ENZYMEX? Go to Wiki Software, click Try EMS Mix. 3 ways you can do here. Find optimal mix and the software will generate optimal enzyme ratio that you can try. You can input the result of your experiments OD600 to compare the result. Suggest new experiments to find 3 enzymes for you to try. This one prioritizes high uncertainty regions where new data would be most valuable. Hopefully, the data can be used to train the ML model even further. Click Add Experiment. Adjust experiment. Change reaction time and click Predict for biofilm prediction degradation. It will give you predicted interval and uncertainty based on random forest ML model. Below are the chart that you can see after entering control OD600, as comparison the predicted and actual values. You run the suggested experiments, feed the results back, and the model gets smarter with each cycle. The takeaway is clear. We have created more than a prediction tool. It's a scientific co-pilot that makes the research loop faster, more resource efficient, and ultimately more effective.
Throughout this iGEM journey, we devoted much of our effort not only to experiments in the lab, but also to understanding the real-world context of biofilm infections, from clinical needs to public concerns, biosafety, and also the future translation. At the very beginning of our project, we wanted to know whether our idea could really matter in a clinic or not. So, we started by interviewing 2 orthopedic surgeons about periprosthetic joint infections in total knee arthroplasty. They told us that although PJI is relatively rare, when it happens, it brings devastating consequences for both patients and doctors. These gave us confidence that our project had real potential for clinical impact. But medicine is not only about doctors, it is also about society. To understand how people perceive biofilms and biotechnology, we conducted a public survey and interviewed professors in medical humanities. What we discovered was a big knowledge gap. Most people had never heard of biofilms, and their number one concern about any new biotechnology was safety. That brought us to a next step. We consulted infectious disease doctors who raised strong concerns about using E. coli as our enzyme carrier. To tackle these challenges, we reached out to biosafety experts and began exploring alternative strategies. These conversations shaped the technical design of our project to make it not only innovative but also responsible. At the same time, we felt the responsibility to bridge the knowledge gap we had uncovered. We organized microbiology workshops for high school students, created short reels on social media, and even built a simple educational game. Through these activities, we made the idea of biofilm more approachable to public, and in turn, we also learned how to communicate science more effectively. Besides, to be impactful, we reflected on what it would take to translate our design into real-world applications. We joined the university's innovation program and consulted both entrepreneurs and professors experienced in technology transfer. These discussions help us recognize the challenges of commercialization and refine our direction, envisioning biofilm as a biologic that supports post-operative antibiotic therapy rather than a fully low-invasive treatment. While still in the early development, this shift gave us a clearer, more practical path for future research and application. Together, this journey from validating clinical needs, understanding public concerns, addressing safety, educating society, and finally exploring translation shaped our project beyond the lab and reminded us that science is not just about discovery, but about making an impact.
In the future, we aim to strengthen our work by optimizing enzyme production, expanding our enzyme database, bridging academia and industry with new insights, and exploring its expression or powdered enzyme systems for surgical use, making our project truly impactful against biofilm infection in clinical practice. This is iGEM NCKU Tainan. United, we take on the challenge of biofilms, not only with experiments but with people. Let's say goodbye to biofilms and hello to a healthier future.